This is your third lecture and the final one for solving trig equations. And I just call this one oddities. These are just the weird things that could happen with period changes or ones that we can actually use our graphing calculators to find. So once you finish these, then you should be ready to do some practice tomorrow. Make sure after this video lecture you fill out the reflection form where you can ask me whatever questions you need to about the trig identities that you're working on. The first one is 2 times the cosine of 3t equals 1. And so just like before, we want to make sure that we're isolating this cosine 3t so that I can start to solve. Know that this is a little different in that I have this 3t in front. So what happens this time is that I actually end up solving for 3t instead of just t alone. Otherwise, things work the same. Let's begin by dividing both sides by 2. So then I have cosine of 3t equals 1/2. And if I want to find 3t, then I have to get rid of cosine. So essentially I'm using the cosine inverse function on both sides. And this will allow me to get rid of the cosines here. So I end up with something that says 3t equals cosine inverse of 1/2. Well, where is cosine 1/2? Cosine is 1/2 at pi over 3, and then again at 5 pi over 3. But notice that's what 3t equals. I'm interested in values for t. Now I want you to recall that the 3 in front of t here gives us a period change in the graph of this function. So we're looking at a graph that has a period of 2 pi over 3. So ordinarily when I was just working with t, I could find that cosine was 1/2 at pi over 3, at 5 pi over 3, and then every 2 pi radians after that, because that's how often the cycle repeated, every 2 pi. Now our cycle is repeating every 2 pi over 3 radians. So we have to consider that as we are looking for additional values. But first let's finish this out and divide everything by 3. If I divide by 3, then t equals pi over 9, 5 pi over 9. Now if I were to apply this every 2 pi over 3 period that I have, this wavelength that I have, or this frequency of the wavelength that I have, then I can translate this and start to find some other angles. So if I took pi over 9 plus 2 pi over 3, I can treat 2 pi over 3 as 6 pi over 9, so that becomes 7 pi over 9. And then I can take 7 pi over 9, add 2 pi over 3, or 6 pi over 9. That'll get me to 13 pi over 9. If I add 16 pi over 9 again, I'm at 19 pi over 9, and that's past 2 pi, which is 18 pi over 9, so I'll stop there. For 5 pi over 9, that's one of the instances. If I add 2 pi over 3, which is the same as 6 pi over 9, I'll end up at 11 pi over 9. If I take 11 pi over 9 and add 2 pi over 3, then I'll end up at 17 pi over 9. So if I am between 0 and 2 pi, here are the values that I have. I have pi over 9, 5 pi over 9, 7 pi over 9, 13 pi over 9, 11 pi over 9, 17 pi over 9. That's all if I'm working from 0 to 2 pi, not including 2 pi. If I want a general equation, then t becomes pi over 9 plus every 2 pi over 3 radians. Notice that that matches this period change that we have here. But I would also find values at 5 pi over 9 plus 2 pi over 3n. And of course, n is an integer. And this would represent solutions between negative infinity and positive infinity. In this next example, we have 3 times the tangent of x over 2 plus 3 equals 0. Keep in mind that x over 2 can be written as 1/2 x. And keep in mind that the original period for tangent is pi. So I'm going to have a period change that's pi divided by 1/2, which is 2 pi. So I have to keep this in mind as I'm finding new angles for both the specific values of x as well as a general formula for values of x. So as we proceed to solve for x, we want to isolate the part that just has tangent of x over 2. So that's going to require me to subtract 3 from both sides, as well as divide both sides by 3. So I have 3 tangent x over 2 equals negative 3. And then dividing both sides by 3, I have tangent of x over 2 equals negative 1. And so now you want to think about where are the places where tangent is negative 1. Well, tangent's negative in both the second and fourth quadrants because sine and cosine have opposite values. So in the second quadrant, we have pi over 4, and in the fourth quadrant, we have 7 pi over 4. So if I do the inverse tangent of both sides, I have tangent inverse of tangent of x over 2, and that's equal to the tangent inverse of negative 1. Then I have x over 2. I can find values at 3 pi over 4 for the second quadrant, 7 pi over 4 for the fourth quadrant. And that's all I can get as long as I'm on a scale of 0 to 2 pi. However, when I now multiply these by 2 because I have to solve for x, I find that x is 3 pi over 2. And I can also find this at 7 pi over 2. Now be careful with this because 7 pi over 2 does not fit in our domain of 0 to 2 pi. So if I'm wanting to go only from 0 to 2 pi, then the only solution I can use is that where x is 3 pi over 2. However, if I want a more general solution, then I can use that x is 3 pi over 2, go back and pick up the period of 2 pi, and I'll know that's how often I'll see changes. So it's 3 pi over 2 plus every 2 pi radians. Again, that's where n is an integer, and that represents values on the range of negative infinity to positive infinity. Okay, this last example, I have x equals 2 sine x. I want to show you how we can work with these just through graphical methods. So if in your graphing calculator, you will place the value for y1 to be x as if you're graphing, and in y2 type in 2 sine x. Make sure you are in radian mode, and you're going to be looking along the window of 0 to 2 pi, which means after you graph, you can do a zoom followed by trig, and that will set your graph to go from 0 to 2 pi. Now I've done this on the TI Inspire, and so what you see as far as the pictures are going to be slightly different from what you would expect otherwise. So this is what it looks like when we graph. The red line is the graph of y equals x, and the green line is the graph of y equals 2 times the sine of x. And so when we want to know where these two functions are equal to each other, what we're really looking at are their intersection points. So once you have these on your calculator, you can then use your second calculate intersection function to help you find those 3 intersection points. And remember, we want to stay on the range of 0 to 2 pi. So this intersection point here at the bottom will not count because we have an x value that's actually less than 0. So we'll only focus on the one here, which appears to be at the origin, and the one to the upper right. And so if you use your intersection function to help you find those, then you'll be able to see where these two actually overlap. So if we look here at the bottom left, this is one we're not including. This is at negative 1.89, negative 1.89. But again, that doesn't fit within our interval of 0 to 2 pi. The one in the middle here is at 0, 0. And then the one at the upper right is 1.895 to 1.895. And so how do we write our solutions? Well, if we're going from 0 to 2 pi, then x can take on a value of 0, or x can take on a value of 1.895. That's again assuming we're going from 0 to 2 pi. However, if we're going from negative infinity to positive infinity, then I actually have three values, negative 1.895, 0, and 1.895. Those are the only places where the graph of x will cross the graph of 2 times the sine of x. So hopefully this gives you a little bit of insight to help you work with your problems tomorrow in class. As always, email me, send me comments on the blog. Whatever you need, ask me a question, and then I can pose my question back to you through email. So good luck with this, and again, try your best. You guys have been doing really good this week. Make sure you fill out the reflection form so I know what feedback you need from me to help you move forward in your understanding. Have a great evening.